All right, we should start again with the last talk of the morning session. And we'll welcome Jongbaek Song, who will talk about integral cohomology rings of toric surfaces.
Okay, thanks for the introduction. And thank the organizers for giving me this opportunity. My microphone is on. It's close enough. Is it okay?
I can hear it, but you put it back.
Yeah. Okay. I can speak loud. So if you look at the title of my talk, it consists of two keywords. One is the integral cohomology and the other is toric surface. So by integral cohomology, I mean the toric singular cohomology of whatever the variety is over integer coefficient. And toric surface, complex two-dimensional toric variety. So as many of you already know, the complex one-dimensional toric variety is just a C-star, complex plane, or projective space. So somehow, complex dimension 2 is the lowest dimension which you can think of, except for those trivial cases. Everybody understands what integral cohomology is. But if you combine these two keywords, it is non-obvious question. So what makes the reason why the problem is complicated is mainly because the fact that toric surface is in general singular variety. But there is a chance that to deal with it because toric surface is a singular variety, but at worst orbifold singularity. So there is a chance to attack this question. So okay, so this is my joint work with Shin Fu and Larry So there. Okay, so let me begin with our favorite example of the weighted projective space. This is the integral cohomology ring computation of the weighted projective space. So if you look at this group structure, then it's exactly the same as the usual projective space. In each even degree, we have rank 1. And there's the base generator, let's say W1 is the degree 2 generator, and then Wn is the degree n generator. So if you just look at the group structure, there's no way to distinguish between this weighted projective space and the usual projective space. However, if you look at the ring structure, there is some divisibility. So in other words, if you multiply the degree 2i generator and then multiply degree 2j generator, it doesn't go to the degree 2 times I plus j generator. There's some divisibility, okay? And also, not only that, but also this divisibility Cij, there is some way to compute straightforwardly from the given weight. For instance, if you look at the weighted projective space with weight 1ab, then the divisibility is nothing but the product of these two weights, A and B, okay? So we are in the toric geometry, toric topology conference. So in terms of the toric geometry, you can think of the fan corresponding to this weighted projective space, right? And then because I have the weight 1 here, right? It's hard to control, so this is 1. So I can assume that there is one smooth cone here. And then the only ingredient which determines the weighted projective space 1AB, just extra ray, right? So obviously, this fan determines the weighted projective space, and this extra ray determines the ring structure of this weighted projective space. Okay, so the question is pretty simple. So fix one smooth cone, and then increase the extra ingredient. That will give you some toric surface, two-dimensional, complex two-dimensional toric variety, right? So we have X sigma, and then there's an object integral cohomology ring of this toric variety. There should be a way to compute the cohomology ring in terms of this A1 type, A1, B1, A2, B2, and AN, Bn, right? This is the question, right? So pretty simple. So let me be more precise about the toric variety. Because we are assuming the existence of the smooth cone, right? So in this particular case, the integral cohomology ring has no torsion, and second degree is exactly the number of rays as an extra rays, except for the rays forming the smooth cone, and there is a rank 1 degree form. Okay, so the question is pretty simple. What is because we have this rank n, so there should be some basis, right? So what is the basis in degree 4, degree 2, and degree 4? And then we can think of the product structure with respect to this basis. Okay. So like if you combine this degree 2 basis in the element u1 through un, and then there should be some integer Cij, which is the multiple of degree 4 generator. And I want to find some concrete formula how to obtain Cij in terms of those vectors, right? Just like weighted projective space. Okay, so here's our theorem. If you look at the toric surface associated with the fan, which I described before, and then there is a nice additive basis, u1 through un in degree 2, and then in degree 4, one generator, such that when you multiply ui and uj, there's some divisibility ai bj. So right. So this is our formula. Okay. So pretty straightforward somehow. Okay, so this is the degree. This is this is the toric surface case. So there is it's commutative, right? So product structure is commutative because of the degree region. So it's a symmetric matrix, and all the diagonal element is nothing but the product of the entry, first and second entry, and the off diagonal entries is something like A1 times B2, A2, A1 times B3 or something. Yeah.
Just to clarify, so your assumption is that there's one smooth cone, or what? Right. What is that? That's the only.
Yeah.
That's what it is.
Yeah.
Oh, okay.
Yeah. So maybe I can remark one more thing. So if you do not assume this one, then there is some torsion in H3. So that makes the situation a little bit more complicated in general. Yeah. Yes, exactly. Yes. Right. So here's an example. So let's think about this then. And the way how you think of the singularity is just to calculate the determinant, right? So except for this cone, the other three cones are all singular. So this is a singular toric variety. And according to our theorem, we have two generators in degree 2 and one generator in degree 4. And the multiplication structure is nothing but if you square the u to the first generator, is the product of 2 and minus 1 here, right? And the square of the second generator is a product of a minus 1 and 2 here. And then product of u1 and u2, that is the product of the first coordinate and second coordinate here. So my product matrix is something like this similar symmetry matrix. Okay. So any questions so far? All right. So now I gave you the motivation of my question, and then I give you the formulation of the question, and then I give you the theorem and the example. So I'm happy to finish whenever I want. So I'm not going to make more sacrifice. I'm not going to sacrifice our lunchtime anymore, okay? All right, so for the rest of the time, I will explain how we came up with this, this nice looking formula, okay? So here's the little preliminary of the cohomology ring computation of the toric variety. So for the case of small toric variety, there is Danilov and Yukevich. They introduced, they studied the cohomology ring structure, which can be realized as just a polynomial modulo sum ideas. So in this case, the equivariant cohomology is isomorphic to the Stanley-Reisner ring, as many of you already know. And this idea is a so-called Stanley-Reisner idea. And the singular cohomology, because the small toric variety has vanishing odd degree cohomologies. So this is the singular cohomology can be obtained from the equivariant cohomology. In this case, the Stanley-Reisner ring, modulo some linear, there's some linear relations coming from the, which you can easily obtained by the geometry of the fan. Here's one remark. Each of these generator in this Stanley-Reisner ring here, so if you look at this X row, that is the Poincare dual of the torus invariant divisors, okay? And also, for the case of obifold, we do not have this Poincare duality in general, but we still have a Poincare duality over the rational coefficient. Okay, so there is the region, there is the critical reason why we can still work on obifold over rational coefficient. So this formula works for the this formula, like Stanley-Reisner ring modulo linear relation, that works for over rational coefficient. Okay? But this is not actually what I'm going to do because I want to work over integer coefficient. All right. So for instance, if the sorry. What is this? Sorry. Okay. So for instance, if the fan, which I showed you in my previous slide, this is an obifold. So over rational coefficient, we can easily obtain the ring cohomology ring structure by this way. So this is Stanley-Reisner ring, which means the Stanley-Reisner ideal is obtained by the product of the first and third and second, fourth. They do not form a cone. So this is the element in the Stanley-Reisner ideal. And this linear relation is nothing but the 2 times x1 minus x2 minus x3 plus 0 times x4, something like that. Okay. All right, so for the case of obifold, I and my lovely collaborators, Showman and Tony, we worked on some integer coefficient cohomology ring computation for the case of toric obifold. Assumption is if you have done toric obifold vanishing odd degree cohomologies, then you can realize this equivariant cohomology as a certain subring of the Stanley-Reisner ring. Okay, so we call this weighted Stanley-Reisner ring. And because of this assumption, odd degree cohomology vanishes. A singular cohomology can also be obtained by the equivariant cohomology modulo sum relation. So this singular cohomology is isomorphic to the weighted Stanley-Reisner ring modulo certain relation. So for the rest of my talk, I will denote this one by WSR bar and sigma. Okay. So I'm not getting into the details of the weighted Stanley-Reisner ring, but let me give you some information about this object. Okay. So first of all, if you look at this weighted Stanley-Reisner ring, then degree 2 part is nothing but the torus invariant Cartier divisors. Okay? So this is basically certain subgroup of the torus invariant value divisors. This corresponds to the just degree 2 part of the Stanley-Reisner ring. Okay. And also, if you remember the Stanley-Reisner ring, it is generated by degree 2 element. Okay. However, this weighted Stanley-Reisner ring is not generated by degree 2 element. Okay, so we have to work with degree by degree in order to find the generator. And also, because of this reason, it is rather tricky to find generators or bases degree by degree, it requires some case by computation. There is no concrete, we do not know, unfortunately, we do not know any concrete formula, but we can, once we have a concrete format of the fan, then we can work with it. All right, so, here, yes. Yeah. Yeah, yeah. So it's not. That's exactly. Yeah, thank you for this comment. So it's not just an assumption. We have a concrete sufficient condition to satisfy this condition. So there is a yes. All right. Thank you, Tony. Okay, so speaking of this weighted standardizing ring, this is some example of the computation. So this is the fan of the weighted projective space, right? Degree 2 generator of the weighted standardizing ring. This is generated by this element, and the degree 4 generator is this generated by these elements. So it looks a little random to you probably, but that's okay because I didn't give you the precise definition. Just believe in my computation. And this is but these two things are something about the equivariant cohomology ring. So in order to get this ordinary cohomology, we need to model out by the ideal J. But in this case, what is the ideal? This is nothing but the A times x1 minus x2 and the B times x1 minus x3. Okay, so this is my idea. And if you apply this idea, then you can reduce this generator by this way. Okay, so for instance, if you look at this degree 2 generator and then this agrees, right? So you can kill this generator in degree 2 part, right? So we only have this generator, and then this kind of computation, this degree 4 part, you can just write down and then take some time, like 5 or 10 minutes, then you can obtain like this is the generator. Yes.
So in this case, if you take A equal to B, you just have CP2.
Yeah.
So do you have any assumptions on your weights? Then when you write this down, in this case, do you assume, what do you have to assume here, that A and B are co-prime or something like that?
Oh, yes, A and like this? A comma B is a primitive vector.
Oh, okay.
Yeah,
okay.
Yeah.
Okay.
Okay. Thank you for the comment. Yes. Yes. By fan, I'm thinking of the primitive vector for generating this one-dimensional array. All right. Okay. So, any questions so far? Okay. So, yes.
Can your like generators be expressed as some minors of determinant of a matrix in which you put the generators and the variables x1 to x like m?
I would say that for the case of weighted projective space, probably there is a way to do this, but for the general surface, I'm not so sure.
Okay, thank you.
All right, so sorry. So this WSR bar is a singular cohomology, and then I have degree 1 generator in degree 2, and then 1 generator in degree 4, and then everything is just a polynomial computation. So product structure is pretty easy to think of, right? So I'm just looking at if I want to the square of the degree 2 generator like this, then I'm just taking the product of these two as a polynomial element, and then think that is going to be a square, b square, and the x1 to the square, and then applying this ideal J, then this is same element as a times b, ab times x2 and x3, right? So remember that Kawasaki formula gives us the ab divisibility, right? So this is another way of looking at the Kawasaki's divisibility in terms of the weighted standardizing ring computation, right? All right, so this is the story number 1. Let me give you the story number 2. So this is probably Tao Gong's talk. He already introduced the topological model of the toric variety. So if you have a toric variety, projective toric variety, and then P is the moment map, the image of the moment map, then whatever the variety is, underlying topological space can be constructed in this format, like P times torus modulus relation. Okay. So here's an example. I'm not getting into the details about this equivalent relation. Probably many of you already understand. But here's a pictorial description. So if you think of this pentagon example, then my lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, this labeling is the primitive outward normal vectors supporting, corresponding to the facet, the hyperplane supporting each facet, right? So because this polytope is an element, is a subset of this dual Lie algebra, so I can think of this lambda 1, lambda 2 as an element in the Lie algebra. So each of these elements gives you some circle subgroup generated by this lambda 1 direction, right? So first I think of the product of this two-dimensional torus, because I'm looking at the two-dimensional polytope. So I take a product of the torus. This is some object before I take this quotient. And then the way how I'm collapsing some part of this space is think about the lambda 1, the circle subgroup generated by lambda 1, and then I'm going to collapse lambda 1 direction circle subgroup from this torus, right? And then something like that. And then do the same business for other part. But accordingly, if you look at this vortex, I'm collapsing this lambda 1 direction and lambda 2 direction at the same time. So that goes to just a point, right? Because they are linearly independent. So finally, I have some picture like this, right? Nice looking picture. It took some time to draw this picture, by the way. So, anyways, so this is an overview. Okay, so what is good for this picture is something like this. You can see some orbifold structure from this picture. So this is a pentagon, and this is the picture I drew before. And then if you look at some local neighborhood of this vortex, then according to the previous topological model presentation, that gives me some neighborhood times torus modulus relation given by lambda vector, right? And then if I compare this presentation, because this UV is homeomorphic to R2 positive, right? So I can compare the standard presentation of the C2, that is nothing but the R2 positive times T2 modulo the standard relation, right? So I can compare these two, then there is a natural surjection from here to here, right? And then because my lambda 1 and lambda 2, they are just linearly independent, right? So torus map given by these two vectors, exponential of lambda 1 and lambda 2, it has some finite corners. So I can compare these two presentations, then you can see that this is homeomorphic to C2 modulo some finite corners. This is one way of looking at the orbifold chart from this picture. Second one is more interesting. So this is
more complicated than the mathematics.
Yes. So if you look at this C2 modulo finite group. This G acts on this C2 linearly. So preserve the distance from the origin. So I can think of the certain some local neighborhood of this zero origin, and then look at the boundary of this neighborhood. That gives me the sphere, odd-dimensional sphere, three-dimensional sphere modulo some finite group action. So this is a cone of F3 modulo finite group. So I can think of this picture like if I decompose this pentagon picture into two pieces, like I am just to fix one vertex, and then think about the local neighborhood like this, and then rest of the edges, right? Okay, I just decompose into two parts. And then my original picture is the union of these two. So that gives me certain co-fibration structure, right? Because there's a sphere modulo finite group, and this entire picture can be realized as a mapping cone of this attachment, right? So I have certain sphere modulo finite group and wedge of two spheres, and there's a map from here to here, and then my toric variety XP can be understood as a mapping cone of this map. So there's a co-fibration structure. Okay, right. So let's go back to our original setup. Okay, so this is my, yeah. So this is my toric variety. This is the fan giving my toric variety, right? And then according to the polytope picture, I can convert this picture into polytope level like this, because just looking at the polytope having out of the normal vector as all this primitive normal vector for the rays, then because I'm considering the existence of the smooth vertex here, so my co-fibration, right? So my co-fib, there is no finite group, so it's just a smooth cone, right? So there's no finite group action. So my co-fibration is now not S3 modulo finite group, just S3. Okay, so S3 to wedge of two spheres, and my up to homotopy, my toric surface can be understood as a mapping cone of this one, right? So now we are very close to the integer coefficient cohomology, because this co-fibration structure gives me homology generator, right, in degree 2. Each of these corresponds to the S2, right, in degree 2. And then degree 4 generator coming from the cone of S3, right? So this is the integer homology basis, right? And also there is no torsion, everything is just free. So it is free to take the Kronecker dual of this basis, which gives you the integer cohomology basis, right? So remember that our famous presentation of the cohomology, we take the Poincare dual, which only for the rational coefficient. However, we are working on this. Everything is free, so we have degree 2 generator and degree 4 generator, and they're taking just a Kronecker dual, right? That gives me the integer coefficient cohomology basis, like this, right? So I have U1 and UN and V in degree 4 generator, and the UI. The pairing with UI and S2J homology class, and they take a product, canonical product that gives him the Kronecker IJ, delta IJ, right? That relation. All right, so any questions so far? Okay. So here is the summary. Tony? Sure. Yeah. Like iterated Tom space or something like that. Yes. Okay, so here is the summary about this question. So I begin with some toric surface, and I gave you the two different stories. One is the standardized presentation, and the other one is cellular presentation. Like cellular presentation coming from the co-fibration, right? But there's a good thing and bad thing for each of these stories. So one is, if you look at the standardized basis, right, coming from the Poincare dual, blah, blah, blah. Oh, sorry. Then this is easy to see the product structure, because everything is just a polynomial, just a product, right? But it's rather hard to find the basis. It requires some case-by-case computation. However, if you work with the cellular basis, it is easy to find the basis, right? Just coming from the co-fibration. However, it is not straightforward to look at the product structure of this basis. It's not clear yet. Yeah.
I mean, the attaching maps will all have degrees.
Yeah.
Coming from the weight, so you should be able to get some information.
Yes, exactly. Yeah, somehow, yes, that's true. Yeah. Okay, maybe. Okay, my lovely collaborators. We can talk later. Yeah. Yeah, but I can give you some little bit more about the homotopy theoretic computation, because this is nothing but the pi3 of wedge of spheres, right? So there's a computation. So you can think of this, you can think of the multiplicative structure by Hilton-Miller theorem or something like that. So you can Hopf component and Whitehead component, something like that. But it's not straightforward to calculate from my viewpoint. So here is the summary. Oh, sorry. So here is the summary again. So each of these stories has a good point and a bad point, right? So as I told you before, sorry, what is this? As I told you before, there's a good point is a standardized basis has an easy to see the product structure, just the product of the polynomial ring, and how to find the basis. And this is easy to find the basis. However, it's not straightforward, the product structure, right? So why not we combine these two good points, right? It's easy, right? So luckily, for the case of weighted projective space, it is good in many sense, of course, because if you look at the standardized basis, then we know this presentation as an example which I showed you before. And then if you look at the cellular basis, then I have a co-fibration like this, and I have the cellular basis like this. But they are just some different presentation of the same cohomology ring. And I have degree 2 generate, only 1 degree 2 generate, and I have only 1 degree 4 generate. So there should be some relation, right? This and this, and this and this, right? So I don't need to think about which one is the linear combination of the other because they are just one generator. So because they are rank 1 and rank 1, I can associate this generator with this cellular basis and this generator with this cellular basis. Of course, there's some subtlety of the orientation problem, but there's a way to pick up some nice orientation to match up. Okay, so this is one. This is one example which can be which has a nice association with the cellular basis and standardized basis. Okay, right. So let's think about the general case. So in order to look at this general case, Shin and Larry and I, we looked at the toric morphism. Okay, so what is the toric morphism? You can think of the map from a fan to the other fan, and in order to make this, in order to this fan morphism to be a toric morphism, what is that? So if you have a cone, the image of the cone should be inside another cone, right? So in this case, the particular toric morphism which we look at is, if I begin with this fan, then I can think of just forgetting all the other cones which I'm looking at, right? Except for one ray, I can forget everything. So that is a well-defined toric morphism because if you look at this cone, that is included in some other cone, right? So something like this. And also, whenever you have a toric morphism like this, then it defines a morphism between two toric varieties. Okay, so we have a, but many of you can see that this is a toric variety and this is the toric variety, the fan for the weighted projective space. So there is a natural map from the my toric variety to the weighted projective space.
Now it slows down.
Yeah. Okay. So we have a map from the my toric variety to the weighted projective space. And also we can show that this toric morphism gives me some at the map from at the level of cohomology. So I have a map from the cohomology. In this case, the cohomology of the weighted projective space and the cohomology of my toric variety, right? Just a perfect. And then remember that each of these toric variety has a presentation of the weighted standardized ring. So there's a nice commutative diagram. Okay, so cohomology ring and the standardized weighted standardized presentation, and there's a nice commutative diagram. Okay, so here's the lemma, right? So if you have a toric morphism like this, then this is the technical lemma, like how the general, because we know all about this weighted projective space case and how each of this generator goes to the standardized presentation of this toric variety, that is this computation. Okay, So let me show you my main theorem again. So this is the fan. This is the fan which I'm looking at, and then I have an additive basis U1 and UN in degree 2, and then now probably you know what these UIs are, and then what this breeze is. Okay, so cellular basis, take a cellular base, homology basis, and take a chronic dual. So that is my U1 UN. And then my product of this UI and UJ, that's going to be AI times BJ. And then now I have pages 16, and the rest of the page is the explanation how I came up with this AI and BJ. Okay, so for the case of weighted projective space, this is probably to repeat my example again. So in this case, I have a basis U and V coming from the co-fibration, and then I have an association like U goes to this one and V goes to this one. So U square to be this one, and then just following the diagram, and then I have this A times B divisibility here. This is what is happening for the weighted projective space. For the case of, okay, so this weighted projective space computation gives me the diagonal element. Okay, so let me show you my theorem again. So if you look at this one, then I'm looking at this product structure in terms of the square matrix, right? So UI, so IJ entry, for instance, IJ entry is the product of UI and UJ. That's the divisibility for IJ entry, right? So this diagonal element corresponds to the square of each of this generator, right? So this, in order to get this diagonal element, I'm just looking at the toric morphism from this toric variety to this toric variety, okay? And then this toric variety, this toric morphism in terms of our co-fibration interpretation, that is nothing but, so this above co-fibration is the co-fibration coming from this fan. And this below co-fibration is the co-fibration coming from this fan, right? And then I have the same S3, but in the middle term, I'm just a pinch, except for the sphere which I'm looking at. Okay? And then each of these co-fiber has this co-fiber. There's a map from this co-fiber to this co-fiber, coming from these two maps. So this is the geometric part, and this is really homotopy theoretic part. So because I have a toric morphism from the toric variety, my toric variety to the weighted projective space, I can just pull back at the cohomology level. That gives me this diagram, right? So I have a cohomology pull back, and then each of this cohomology has a presentation of this weighted standardizing ring, right? Like this and like this. So therefore, I can just think, I can begin with this. If I want to look at the square of this element, I just chase the diagram like this. So if I have a UI, that corresponds to this class, right? And then take a product, and then I know how to take a square for this particular element, because this is the world of weighted projective space. Okay. So this is the way how I came up with this AI BJ is a diagonal element of my matrix. For the off-diagonal element, it is a little more tricky. Like if we begin with this one, then think about the same toric morphism, right? Except for two rays, which I want to take a product, right? So, oh, sorry. So yes, so begin with this toric variety. I just merge all the other cones except for two primitive rays which I'm looking at, and then another toric morphism from here to here, right? Okay. So the previous fan diagram in terms of the co-fibration diagram, that's going to be like this. So each of this vertical rays, there's a co-fibration of my toric variety, and this is the middle toric variety, right? And then this is the vertical line. Horizontal lines are just a pinch map to just go to the point, right? And then I have a projection to here to here. right? And then, so from this toric variety, I have some intermediate toric variety having second Betti number is 2, right? And then from here to I have a weighted projective space and another weighted projective space, right? So this diagram gives me the diagram for the cohomology, right? So everything's just a pullback. So I have a cohomology of my object and the cohomology of my intermediate object, and then cohomology of the weighted projective space and weighted projective space. And then each of these first floor goes down to the presentation of the weighted Stanley-Reisner ring, right? Which you can play with just a polynomial ring. Right, so in order to find the basis of the Stanley, my original toric variety, I can begin with this weighted projective space. So it has a cellular basis, UI. I'm just, in order to distinguish the basis of this one and this one, I just put triangle, right? So weighted projective space, and then square, right? Second Betti number is 2, everything square. So I have 1 degree 2 generator and 1 degree 4 generator, and the same as this one. And it goes to this element and this element at the world of weighted Stanley-Reisner ring, and it goes to this element, and these two blue and red gives me the 2 degree 2 generator in the intermediate object, right? And then I can, now I have some association like this because I have a Stanley-Reisner presentation for this element, Stanley-Reisner presentation for this element, and according to my technical lemma with how the Stanley-Reisner weighted Stanley-Reisner element maps to the other presentation of the weighted Stanley-Reisner ring, then just applying that lemma, I have an element like this. Okay, so now I have a basis here. I don't know how to compute this one at the level of cellular basis, but if you go down to the weighted Stanley-Reisner ring level, I can easily calculate. Right? So it goes to here, this one goes to here, and then take a product. That is nothing but the AI times Bj. That is the way how we came up with this formula. Okay, so yeah, so just by diagram chasing, I have this one goes to here and this one goes to here for the original toric variety. Right? Okay, thank you very much.